Okay, so this is SIT215 Investigation Reinforcement Learning PBL4. I'm Gia Phu, and this is my talking about this task. So table of content. In here, I will talk a little bit about introduction about mathematical reinforcement learnings. Next, I will talk about the taxi problem and the carpool problem, and I will comparison between the two problems. And finally, I will talk about frozen lake problem where individual chosen environment. So first of all, I will talk in fast about mathematical reinforcement learning. So reinforcement learning is model-free it's a method to act for using reward systems to mimic the way humans or animal learning new things. So like you training a dog, right? You give him reward when he's doing the right things, and you give him penalties when he's doing the wrong things. Reinforcement learning is also like that. Too many try and error, it automate the judgment based on previous experience, and and reward systems, and they have a reward system to determine whether to give a reward or penalties, depend on the value. One of the important algorithm that making reinforcement learning is market decision process. Market decision process is a tuple where it have a state, a finite set of state action, a finite set of action, the transition of state, the discount factor, and the reward to determine so it gets to determine kind of what's happening, and making a tuple and form a SQL decision. So it helps like form a SQL decision process, and to determine to construct the value function for a given policy, we have Bell equation. This is not the final state of Bell equation, but I imagine this would be a nice example of what we are trying to accomplish. So a market decision process state value function is have a function v policies is expect to return from beginning of state S, and the policies is implement using this Bell equation, right? So temporary different learning. Temporary different learning is a model-free reinforcement learning approach. It is an unsupervised type method to predict current and future reward based on the current policy that we have. So in here, I will use two algorithm. First, Q-learning is an op policy, and use greedy policy to maximize the reward for the next, to maximize the reward. The purpose is to maximize the reward, and value iteration. The purpose is to optimize the market decision process policy and its corresponding value. So furthermore, the taxi problem. Yeah, we'll have a quick look up what's happening. The taxi problem is like this, where you have a taxi, a passenger, and a grid environment. The agent would be the taxi, the environment would be the parking lot, the grid right here, the actions. The episode opens when with a taxi at a random play, the passenger at a random play, and the episode ends with the taxi give the passenger drop off the passenger to a right place, right? The action space of this would be six discrete action. It can move in 4 direction. It can pick up a passenger. It can drop off a passenger, and the space stay would be 500, right? It got represented by this tuple, and the report system would be like it -1 when so it means for most steps is the reward is getting lower. It's +20 for delivering the passenger, and when pick up or drop off action illegally, it will -10. So in here we will use random policy and Q-learning. We use random policy in this situation is like brute force. It means try until the episode ends. So as you can imagine, it's not really efficiency, right? It took like 2,000, more than 2,000 time step just to end the episode, and the penalties is like 700. That means 700 times more than drop up and pick up illegally. Right? It took longer time and it's not learning from the past. That's why. And in here we have Q learnings. Q learnings is given a significant better result. Average time step only to 13, right? And it gives it like 0 penalties because it learned from experience. In here you can see that the time step we test in this the training session. The time step the test is getting smaller, less and less, fewer and fewer steps at a time. And this one is the total reward. We can see at first the reward is bad, right? It's like brute force, but then it getting better and better to 10,000 episodes, and when it's got to more than 70,000 episodes, it's got into positive again. So yeah, conclusion, the Q-learning absolutely would be better for this situation because it's showing faster, it's showing the problem a much better efficient, not 2,000 steps. The carpool problem. Furthermore, have a quick look at this problem, right? It have a post and a cart. So you can right here, the Asian is the couple itself. The environment will be this survey. The frictionless survey. The friction is 0 in this case. The purpose of this is to balance the pose as long as possible, like this. Yeah, balance is not getting dropped. So the inputs of it would be a continuous variable. Input of it is the action space. The action space is an array with only one variable. It takes value from 0 to 1 to determine the direction and the force we put in. So the more 0, it means put the cars more to the left and faster and more force. More to 1 is mean put it to the right, more force to the right. And the state which give us we have 4 different variable that determines what's happening. We have car position, car velocity, pole angle, and pole angular velocity. The reward is given +1 for every step we taken, and it's stopped by rendering in this threads in this value between two of this value, and the episode would be termination when the pole angle over 12. It means whatever we do is will drop. When the car position is greater than 2.4, it means it reach the edge of the display, and the episode is and the time step took is more longer than 200. We took 500 episodes. So in here we will compare between random policy. We're still using random policy and Q learnings. So in random policy, I let it run for 1,000 times, and none of them have up to 200 steps, right? Because it's not learning from the past. With Q learnings, we have a lot of episodes reach into 200 time steps, especially after 315 right here. We see a line pretty. It's because it's running from experience, but it's very significantly around 200 episode right here, and sometimes it's still very right here. So it indicates that the learning process of us is not perfect. Right? So we still need to improve, or we can choosing another type of algorithm to provide a better solution for this. Okay, next we will compare between the two problem. Oh my god, I talked too long. So first of all, the input will be also the action space. In taxi problem, it will be this grid, which means it will be 1, 2, 3, 4, 5, 6. Moving up, moving down, moving right, moving left, right. And in car per problem, it will be continuous variable. It means it could be infinite amount of number between 0 and 1, and any of that can be used as the input. The changing state this taxi problem is moving to another index, just moving like you get it up, it's just moving to another square, right? And it's giving out the ever it stays like that. But in the couple problem, it's kind of mimic the real life physics where you put an action, it giving out a continuous state of variables, right? So, and the taxi problem is also easier to end, right? It just need to reaching its goal, and on this we would have to reach a condition, one of three condition like so earlier, or again to more than 200 steps. In that case, we have to stop it, otherwise it would be just keep running until it reach one of three condition. So in conclusion, the couple problem is kind of difficult more for our algorithm to learn, right? So that's why the Q-learning is kind of less efficiency in couple problem, and it would take, and the couple problem would take a longer time to run and train, right? It takes more to determine the time step. Of course, we can reduce the termination time step into like 100, and it would be kind of like half time faster. But yeah, it won't show the significant. It won't show whether we want. It won't show what we want, right? So next up, I will talk about frozen lake problem. It's the problem that I choose. I chose the problem one. This problem is more like taxi problem. Just don't have passenger, don't have taxi, it's just moving, and it's have host. And one of the interesting things is have slippery. Right. So the Asian have when it get to slippery, when it gets slippery, the Asian only have 1/3 of probability. It means 32% of the chance to move into a desired direction. For example, it's got here in the start, right? It's one to move in to the right. So, but because slippery, it may be going to the here, like that. So maybe into here. You want to go here. Because of slippery, it can go into any other direction. 32%. So it can move up or move down. 1/3 of a chance. So yeah, the agent would be the character that's walking, right? The environment would be the grid 4.4 grid. I choose 4.4. The Asian is taking a direction 0 to 3, 0 for left, 1 for down, 2 for right, 3 for up, like this. A sitting state, and the reward would be reach and go is 1. That's all. Reach and go, and you get 1. Episode termination when reach and go. So yeah, and slippery. It can want to go here, but it can go here or here. It can go up or down, kind of like that. So the result. So Q-learning is it. I only trained Q-learning for 1,000 steps, 1,000 episodes, and as you can see, the more at the end, it get easier to be success. And Q-learning seem to impressed because it has success rate of 73%, right? But sometimes it can be fluctuating. This may be because I live in training style too small, only 1,000, but and I can see that it's already enough, right? And the success rate is not only the success rate is 73%, but as we can see in that 25% that's only exceeds 50 steps. 50 steps to go into 4.4 grid. Like why? Right. So yeah, we need to counter that in mind. And moving on to value integration. Value integration is giving me a better result. It's going up to maybe 80% for some time, 80 to 90%. Sometimes it's get to 90%, and the step it takes is clearly less than the quick learnings. Right? It takes easy step, only like less than 20, right? So set for 74%. Yeah. So in conclusion, I would think that value integration have a better result for this, and if I just increasing more episode trainings, value integration will give me a much better result. So yeah, this is the end of my videos. So thank you for watching. Thank you, Lars. I hoping I spent a lot of time on this.